Welcome everyone. Let's have a look at problem 17.2 which you see on the screen right now. In this problem we are supposed to consider again the aircraft example in 11.1 and now tune it with the Hinf command, so basically via loop shaping, and understand the trade-off between tracking versus measurement noise, rejection, and then as a second step understand the trade-off between tracking and input disturbance. So let's start. So let's first look at part A. So for part A we're asked to ignore input disturbances and measurement noise, and the constraints are only on the third channel, third control channel U3. So we assume that there is no noise and no disturbance first, and we will then do a two-block design. Let's see what we mean by this. So we have a loop like this, so that is our loop, and we're looking for a controller K that achieves good tracking. So that's tracking is the only goal for this part. So oh, by the way, this is negative feedback. So a standard thing to do would be to choose the error as one channel with WS as the shaping filter and U. So this is Y, this is U, and this is E, and U as the second channel for the performance measure, and Z as the output performance channel, so R to Z. Now this we can just write in the form of a generalized plant as follows. We have a G and R enters the loop. We have R minus Y would be E, E goes through WS and comes as Z1, or let me just keep it as it is for now. E also goes out for the control measurement. The control U comes in, and so this goes via WK to the second performance channel. I can call this thing Z. R as the input, U as the input, Z and E as outputs. So then the generalized plant would be this one. Let me bring the E outside, and now we are looking for a controller K that measures the error and exerts U on the plant. So this is the generalized plant for this. So by this time you should be familiar with this, and you should find this quite straightforward. So we're looking for a K that minimizes the H infinity norm of the closed loop from R to Z. So let me write this in a different way. So the closed loop transfer function is ws times the sensitivity, because the transfer function from R to E is S, and then we have ws going out in the first channel, and then the second channel is wk times the control sensitivity. Again, from R to E is S, from E to U is ks, and then you have wk multiply. And now the unknown, or the variable, is the controller k, and the sensitivity is obviously also a function of this variable k. So that is the closed loop transfer function. So if someone gives us a k, we can plug it in here and get the closed loop transfer function. So that one. And now we want to minimize the h infinity norm of this and find a k that does that. So this is the problem, and we know that the solution to this problem could be obtained in Matlab with the command Hinf, and you just have to provide the generalized plant to this command, and this is now shown in this code. So here you see the generalized plant that we just defined above, and this is how you define the generalized plant, and then you execute sysic and then the Hinf command. So that gives us a controller k. Now before we execute this part of the code, we have to define ws and wk, which are the tuning knobs. So we have to iteratively select these until we get a design that is acceptable. Now a reasonable first choice at least in shape of ws would look something like this. So if this is the 0 dB line, and we have frequency axis here, what we want is that the S, the sensitivity, should have some shape. So this is log scale, remember, some shape like this. So we saw in some earlier exercise that for some systems we cannot avoid this bulging out of S above the 0 dB line, and that was then called as the waterbed effect. So we want the S to look something like this. So we look at ws as sort of a weighting on the frequencies. So because we want in the lower frequency range a low value of S, we put a high cost on it. So we might want to have ws something like this. So a lower cost on high frequencies and a higher cost, so a higher cost on low frequencies, so that the optimizer tries to push low frequencies down, and a lower cost at high frequencies, so that the optimizer allows an increase in S. Another way to think about this, so this would be ws of j omega, this would be S of j omega, and we are plotting omega on the frequency axis, on the x-axis. Now another way to think about this could be by looking at the inverse filter. So the inverse filter would look something like this, and you can then think of the inverse filter as something that you can use to push the S down. So we can sort of shape the S by selecting a reasonable shape of the inverse filter. So you can then design such a WS, and for this you can use the make weight command, which gives out a first order by proper filter, and depending on the version of Matlab you're using, it takes as input the low frequency gain, the high frequency gain, and the frequency at which you cross the 0 dB line. I think in the newer versions of Matlab you can specify a particular frequency and the value of the filter at that frequency. So you should look at the help command before you really do the tuning. So that's first choice for WS. A typical first choice for WK would be just a constant. I mean, you obviously have to go back and forth when you tune your controller between WS and WK, but you can start with such a standard shape of WS and a constant WK. So now let's look at one design here. Let me bring the filters and the closed loop transfer functions. So this is one design. So this red dashed line shows the inverse shaping filter and WK. So this one, these constant lines show the WK filters. Now note that we have a multi-input multi-output system here. So this part of the code shows the filter design. We use the make weight command, and we have a high frequency so we have a we have a high weight at the low frequency, that is 1E4, so and a low weight at the high frequency, that is 1E minus 2, and the crossing of the 0 dB line at about 150. So that would mean so 1E4 at low frequency and 1E minus 2 at high frequencies. So that would be the 0 dB line, and this would be the shape of WS, and the inverse shaping filter is then what you see here. Now because we have 3 channels, so the output is of the size of ny, and so is the error. So we have to use in each channel a shaping filter. So what we do here is use the same one in all 3 channels, but for the control channel we do a constant shaping filter of 1.2, which is what we see here, 2 straight lines, but we have to sort of present this as a state space model, so that's why I have SS of 1.2. so that's basically just a static system with A, B, C matrices 0 and D equal to 1.2. and now what we do is we multiply the third channel by 3, so we have WK something like this and WS something like this, and that's why you see 2 lines here instead of 1. So the 2 lines with 1.2 and 1.2 are overlapping here, and then the other line is 1.2 times 3. So I would like to reiterate once again that this corresponds to the steady state error. So, or in other words, at at 0, as omega goes to 0, the value of s of j omega tells us something about the steady state error for step inputs. And now we can see here that we have for one direction integral action, whereas for the others we have some constant steady state error, and that is why we push the s down. So if we were unhappy with the steady state error we obtained here, we would then push this down, or in other words, increase the weight on the low frequency values of the shaping filter WS. So push this up. Yeah, so let's look at the time domain results now for this design. So these two plots show the time domain results for reference step inputs. So let me say we have a reference step input or unit step input at the reference, and we have three outputs. So reference step input at the first channel and 0 at the other two channels. So we have that at least the output y. So sorry, this one is control input, and this one is, so that is u, and this one is output of the system, that is y. So we see that for a step input we have almost 0 steady state error. You can see we have a rise time, or let's say a rise time or settling time of about point something less than 1. So we have a settling time of less than 1 seconds. You can check, but I think it's about 0.9 seconds, after which the output is between 1 plus minus 0.1. Yes, and the control input 3 is less than minus 20, or in magnitude less than 20. So that's for the first design, and let's call this design design 1 or something, or let's call this design 2 block design. So where is it? Yeah, so this is the two block design 1. Now so let's look at part B now with this design. So part B now asks us to inject noise. So this design required us to assume so let's look at part B now with the same design. So part B asks us to include a noise now at 10 to the 4 radians per second, a sinusoidal noise, and to see what happens. So let me bring this feedback loop again. Now we are looking at B, and we have measurement noise, and that is sinusoidal at 4 radians per second. So now if we bring this noise in our feedback loop, this was our feedback loop, and now we include noise n here, Note that this will be the same as including this noise here, so this would then be R minus N as the input at this point. So all the transfer functions, so from N to E, would still be the same. So we had S as the transfer function from R to E, and Ks as the transfer function from R to U. We would have the same transfer functions from N to E and from N to U. So except that we have a negative sign here, which we can then just use to define a noise signal, and tilde as the negative of the noise. This is especially not important if you have zero mean noise, which would sort of then have the same transfer function from N tilde to E and N tilde to U as S and Ks. Now once we establish that, we can then go back to our design and the frequency domain plots of the sensitivity and the control sensitivity functions, and see what might happen if we inject a noise along with the reference unit step input. So if we inject a noise of about 10 to the 4 radians per second, the error, which is the output of the sensitivity, would be, so S is almost equal to 1, which means that T would almost be equal to 0, because we have that S plus T's identity. And note that now, because we have multi-input multi-output systems, S here would be identity and T would be the matrix, the 0 matrix. Now this would mean that noise is not affecting or N is not affecting output Y. So that's good, because even if we have measurement noise, we see that at this frequency it is not seen at the output. But now let's see what happens to the control input if we have a noise of, so this one is 10 to the 4 radians per second. We see that for one particular direction we have a significantly high control input. So we do see that we have an amplification of noise to U transfer function. So if we inject a noise, we should see that U is amplified, and especially if we inject the noise exactly at along the eigenvector, or because this is square, now we can say it's eigenvector, but more specifically along the singular vector that excites this this singular value, then we would have a high amplification in the control input. And let's see if we indeed do observe that in the time domain plots. So I have here the time domain plots when we have reference unit step input and with noise at around 10 to the 4, so no, at exactly 10 to the 4 radians per second with some random phase shift. So as we already analyzed from the frequency domain plots, we see that the output Y is unaffected by the noise here, and you see almost an identical output as we saw earlier without the noise, whereas the control input is extremely jittery, and we see that this is because we had one particular direction for which the singular value of the transfer function Ks at that frequency was high, which meant that this would lead to oscillations in the control input U. Now how do we solve this problem? So we would want ideally to not have such a jittery control input U, but we would not want to sacrifice the good performance of the output. So let's now look at the open loop G, open loop transfer function G, and gain some insight there. So this plot shows the singular value plots for G. What we observe is that G has a roll off much before 10 to the 4 radians per seconds. So what means is that if G has an input corresponding to has an input with a frequency content at 10 to the 4 radians per second, that would be attenuated anyways with the open loop dynamics G. So what we can do is that we can ask our controller. So let's go back. So that's our design. We had constant shaping filters for WK, and what we can now do is enforce a roll off in the control action here. So let me use a different color. So we can enforce a roll off of the control action at frequencies maybe much before 10 to the 4, so something like this, so that the control action so what this would do is that this would not make the control input U chitter around when we have an input noise or measurement noise at this frequency. So let's see what we can do for the shaping filter WK. So as a first modification, we try this shaping filter for WK. We keep the WS as it is. So I now show the control sensitivity transfer function or sigma plots here, and we see that for 10 to the 4 or approximately 10 to the 4 we have a singular value of 13.2 dB, which is still quite a lot above 0 dB, and that you can see again via the oscillations in the input, and the output is still almost identical to the one without the noise input. So then the output again is undisturbed, but we do have input oscillations, and the oscillations, now this is the zoomed in figure. So again input, but now we can see that the input is oscillating about 1 with approximately plus minus 0.5 units in the first channel. Now once we observe that, we can then modify the design and push this roll off frequency to the left. So let's reduce this. So now this is the second iteration with a reduced roll off that you see here, and now here you can see that already in this design that at 10 to the 4 radians per second the singular value is less than 0 dB, so at least we don't have an amplification of noise, and this can be seen in the time domain plots here, where we see that the input is oscillating with a much less amplitude than before. You can see the zoomed in figure here, and now the input is approximately oscillating with an amplitude of 0.1. Note that the output is still almost exactly the same, now with slightly longer settling time, and that's because we're essentially making the controller slower. Now with one final modification we could still further reduce this one to see how much we can reduce the oscillations in the input while maintaining the output response. So that's the third iteration. Now here we have only one E1, so, and with an excitation of 10 to the 4, the largest singular value is minus 12.5 dB, which is lower than in the previous iteration. And now we see that the oscillations, again this is the zoomed in figure, we see that the oscillations are about plus minus 0.05 now, or 0.4 let's say. And again the output is reasonably close to the one with our first design, with a slight increase in the settling time. So let's call this design now again two block design, because we are still shaping S and KS, but now with a roll off in K, or let's say roll off in K. And now let's go to part C, where we now bring in input disturbance. So as a first step, now when we consider step input disturbance, let's take the design that we already had, which is the one here, and just inject an input disturbance to see what happens to the output. So this is the response when we have a step input disturbance, and what we see is that we have very large oscillations in the output. So what could be the reason that this is happening? In order to analyze this, let's now look at the transfer functions from D to the error, and from D to the control input U. So let me bring back our feedback loop again. So this was our loop. So let's now first copy it here. So let's remove the shaping filters and bring in a disturbance input. D. Now the noise could just be moved to the reference, and we didn't have any new transfer functions to consider, but with the disturbance entering here, we do have new transfer functions that we need to consider. So let's now derive the transfer function from D to E. So we would have, let's consider plus here, so we would have and let's name this signal UD. So UD is U plus D, and now we have U as nothing but U is nothing but K times, so minus K times G times UD, and then we have the D as it is. So we have identity plus KG UD equal to D, or in other words, UD is I plus KG inverse D. Now this is UD, but we want to find the transfer function to E. By the way, this transfer function is called the input sensitivity, usually denoted by SI, and the usual sensitivity, which is I plus GK inverse, is typically called the output sensitivity. Now yeah, let's go back to what we were doing. So we want to find the transfer function from D to E, so we have up to UD, and now E is just G times minus G times UD. So we have, that is nothing but minus G times I plus kg inverse T. And now if this inverse is well defined, we know from the Neumann series that that is nothing but I plus kg plus kg squared and so on. Let me write the squared as kg and so on times t. Now we can push in the d from the left and pull the g out from the right, so we would have minus again I plus gk plus gk and so on. We've pulled the g out from the right, t, and now this one again from the Neumann series is, and if this series converges, we have this one as I minus gk inverse times g, and this is sorry, so I missed a minus sign here, so I have minus kg, and then I have minus kg times minus kg and so on. Similarly, then if I bring in the g inside, I would have I plus minus gk plus minus gk times minus gk and so on, pulling the g from the right out. And this one now again from the Neumann series, and if this series converges, is I plus gk inverse times g times d, and now I plus gk inverse is just our usual sensitivity function, this one, the output sensitivity, and now therefore this is minus sg times t. So that is the transfer function from d to e. Now up to u, that's easy because u is just ke, so we have minus ksg t. So we have two new transfer functions which we didn't consider here, and that is sg, or to be specific minus sg and minus ksg, and these were from d to e and to u. Now if we look at these transfer functions for our design, so for our two block design with roll-off in k, let's see what they show us. So these are the transfer functions sg and ksg. Note that we are plotting sigma plots which are equivalent to taking the absolute values of sg and ksg for seesaw system, and so the negative sign again here is not of any consequence. So these are the transfer functions from input t to output e and to output u. Now what you see here is that for low frequencies we have a very large error, and this is really the cause for these high oscillations that we saw in the time domain plots here. So this d is which is step in our case, that is being injected at the input disturbance is causing high oscillations because of this thing. Now let's also look at the controller we obtained in our previous design along with the plant sigma plots. So here you see the controller that we obtained for, so this was the 2-block design with roll off in K. Now for this design we obtained a controller whose sigma plots are shown here, and the open loop plant G has sigma plots here. What is peculiar is that we see that at omega, a frequency of 0.182 Hz, we see a peak in G, and at the same frequency we see a drop or a notch in the controller K. What this indicates is that there is a pole zero cancellation, and the pole being at that frequency. So this would be straightforward for Zizo systems, but because we are now talking about MIMO systems, we have to be careful. So what I mean by this is this. So there could be a pole zero cancellation at omega equal to 0.182 radians per second, and this can be checked by getting the G at 0.182 J by using the FREC-RESP command, doing an SVD, a singular value decomposition of G, to obtain these vectors, the singular values. So to get this one, so what we want to get is the input and output singular vectors corresponding to this largest singular value here and to the lowest singular value here. So for the plant it's the largest singular value, so we look at the singular value decomposition of the plant with transposed. So U sigma V transpose, that's what you get when you do an SVD of the matrix evaluated at this frequency, and this value should correspond to 48.8 dB. Note that the SVD gives you a value in linear scale, not in the dB scale. So again, if we then check evaluate the controller at the same frequency and do an SVD for the controller, now for the controller we are interested in the smallest singular value, which is this one, and again this one should correspond to minus 26.9 dB, and with the input vectors of the controller. And now it should be interesting, and I encourage you to see this for yourself, that these input and output vectors should make sure that you have a pole zero cancellation, or in other words you should have, because the output of K is going in as input, so this is the output of K is going in as input to G. What you should see is that if we have Vg1 transposed, Vg2 transposed, Vg3 transposed, which is the right hand side matrix of the decomposition of G at that frequency, times UK1 UK3 should excite or should be almost equal to 100, which would then mean that you indeed have a pole zero cancellation and the directions match. So the point of this part of the exercise was to see that if we do a two block design, we can have pole zero cancellations, and if the G had an unstable pole, and if we do then a two block design, the controller could in principle cancel this unstable pole, and this would be unrecognized in the S and the KS transfer functions, and could lead to a potentially unstable design as soon as we have input disturbances. So the recommended thing to do is to always do then a 4-block design, which I will now shortly say a few words about. So now let's look at the 4-block design, and let me construct the generalized plant now. So we have a G, an input R. Now we bring in two additional shaping filters, VR and VD. So that's VR. We would have error E, again WS, error going out. We have U coming in, WK, the two performance channel going out here, as Z, and now we have an additional input D with shaping filter VD, and that is coming as an input disturbance to U. So that is U, and now we can draw a box around this. So let me bring the Z and the E outside again. So that's our generalized plant, and again as before we are looking for a controller K that measures this error E and exerts a U on the plant. So then now if someone gives us a controller, the closed loop now looks something like this. We have the WS and the WK here, then we have the usual shaping filters S, which now depends on K. We have the S and KS. So this was for the 2-block design, and now we have two more. We have S depending on K times G, and then we have k times s, again depending on k or function of k, times g, or to be specific we would have a minus sign here and a minus sign here. And then we have additional input filters. So this is our closed loop plant, and the goal is then to minimize the h infinity norm of this one, to minimize over all k the h infinity norm of this plant. And again, as before, we can do this now by this modified generalized plant and the hinf in command. So now I will not show the code again, but it's there in the Matlab scripts folder, and you should try to have a look. Now some starting points for the tuning knobs. So ws and wk as before, and we can start with vr and vd as identity, and then iterate by looking at the time domain and the frequency domain plots. So now let's bring in the I will now just show the time domain plots for this design. So what I've done here is that used for ws and wk the design as before, which was the 2-block design with roll off in k, and then set vr and vd as identity, and that gives us the response for a step reference, so r and d, and the output is y and u. So notice that this part is the r to y and the r to u transfer functions, and this part is the d to y and the d to u transfer functions. First of all, notice that the oscillations in D are now gone just by the inclusion of the extra channel D in the generalized plant without any tuning. We do now have a slightly poor performance in tracking as compared to the one before, and that's because we do not have now this pole zero cancellation that we saw, which led to oscillations in D, and this is the trade-off now. So here you see the sigma plots of k, and you don't see the notch anymore at 0.182, which is somewhere this would be 0.1, so somewhere here. So somewhere here, and now you see that the SG, which is the transfer function from D to E, is showing a good lower value at low frequencies, showing a smaller steady state error for inputs. And now that's it. That's all I wanted to present for this problem. You should now go ahead and try to tune the controller and experience for yourself the trade-off that we have between good tracking performance and good input disturbance rejection. So that's it for this problem. Thanks a lot.